Hello students, in last lecture we have seen about the events, the types of events and some identities related to events, that means De Morgan's law or set identities. Then we have seen occurrence of at least one of the events and occurrence of all the events simultaneously. Now let us move towards the concept of probability. Now before going to the concept of probability, let us see the terminologies used in this definition of probability. In the definition of probability, we require the sample space that should be a equiprobable sample space. So what is meant by equiprobable sample space? As the name suggests, equiprobable. Equi means equal and probable means probability. So a sample space in which all the elements have equal chance of getting selected, or each and every element has equal probability of selecting. So the definition is, consider a random experiment which has n mutually exclusive likely outcomes. The sample space omega is said to be equiprobable sample space if all the outcomes are equally likely. Now see, in this definition I have done here in the red color, that is mutually exclusive outcomes. The outcomes in the sample space required is mutually exclusive and here likely outcomes. That means mutually exclusive likely outcomes means what? All the outcomes are independent. We have seen that it's mutually exclusive events. Two events A and B are said to be mutually exclusive if A intersection B is equal to empty set. That means A does not depend on B or B does not depend on A. Their occurrence is totally independent. Same meaning is here, mutually exclusive likely outcomes. For example, when we are tossing a coin. So if I am tossing first coin, I got head. And again I am going to toss the coin. Then what will happen on the second coin, whether it will come head or tail, that does not depend on the first, what comes in the first. So the next trial, if you are going to toss the coin third times, then what will come on the head or tail? That is totally independent what previously occurred. Or here we can say each trial is independent. That means outcome of the next trial does not depend on the outcome of the previous trial. So such trials are mutually exclusive trials, or their outcome is mutually exclusive. And their likely outcomes means all are having equal chance. That means when we have the two coins tossed, that is head and tail, we are getting the outcomes. Then chance of head as well as chance of tail, both are same, that is 50-50%. If we are rolling a die, then there are 6 outcomes. So chance for each one is same, that is 1/6. If there are 10 students in the class and teacher is going to call one student, then chance for is 1/10. So here the chances are equally likely. So that is the definition of the equiprobable sample space. So all the outcomes in this one are mutually exclusive likely outcomes, and the sample space omega is said to be equiprobable sample space if all the outcomes are equally likely. That means they are independent and chance for each one is same. Or we can say the another way, the probability of occurrence of every outcome is same. Now, if omega contains the elements omega 1, omega 2, omega 3 dash dash omega n, these are the n outcomes, then omega is equiprobable means that the probability for each omega I is 1/n. Since there are n outcomes, the probability is 1/n. Naturally, this I lies in between 1 and n, or it may be equal to 1 or n. So probability of omega 1 is the same as probability of omega 2, is same as probability of omega 3, and is same as probability of omega n, and that is equal to 1/n. Now let us see the classical definition of a probability. So if a random experiment results in n mutually exclusive and equally likely outcomes, and m of these outcomes are favorable to an event A, then the probability of occurrence of A, that is denoted by P of A and is defined as P of A is equal to m upon n, that is equal to favorable number of outcomes to A divided by total number of outcomes. That is here 0 less than equal to m less than equal to n. Now see the definition of the this is a classical definition. So random here in this definition is random experiment results in n mutually exclusive. We have seen the definition of what is meant by mutually exclusive, that we have seen. So here mutually exclusive is there. Then equally likely outcomes. That means all the outcomes are independent and each has equal chance. So when we are having such a n outcomes, out of that mr belongs to the event A. Then the probability is m upon n, that is favorable number of outcomes to A, means outcomes belonging to A upon total number of outcomes. Now m, obviously it is lies between 0 and n. When m can be 0, if it is an empty set, then m can be 0. Or if m is equal to n, means all the outcomes of A are equal to omega, that means A is a sure event. In that case m can be equal to n. So the here probability always lies it between 0 to 1, that is 0 is less than equal to A, P of A less than equal to P of A is less than equal to 1. So see the proof of this. We know that 0 less than equal to m less than equal to n from here by definition. Divide throughout by n. So 0 divided by n means 0 is less than equal to m upon n is less than equal to n upon n, and n upon n is 1. But what is m upon n? Here we have seen m upon n is nothing but P of A. So 0 is less than equal to P of A is less than equal to 1. So we can easily say that probability of any event always lies in between the interval 0 to 1. So if there is a question, check whether the given is a probability or not. Then you should check whether it is lies between 0 or and 1 or not. Now when we are applying this classical definition, there are some limitations of the classical definition. Now we have seen that is in classical definition the outcomes are mutually exclusive and they are equally likely. That is the basic requirement in classical definition. Now the limitations of first classical definition of probability. First one is, it is assumed that all the outcomes of the experiment under the consideration are equally likely. That is the basic requirement in classical definition. But does it happens always in the ideal case? No, because we know that probability of passing an examination and failing in the examination are not same. And this is not the case always. That means this is not the ideal case, because we know that if I am going to appear for an examination, if there are 100 students in the class and they are going to appear for the examination, so it will not happen that probability of passing is 50% and probability of failure is 50%. No, if you have prepared for the examination, surely you know that you are going to pass. So probability of pass and fail, that will not remain in the ideal situation. Though the outcomes are same, we know that means when we are tossing a coin, probability of head and probability of tail, that is equal to 50-50% that we are expecting. But same thing, appearing for an examination, outcome is pass or fail. So though there are outcomes are 2, that does not mean that always that probability of failure and probability of passing that is same. So if that is not the real case, so this classical definition will not applicable in such cases. So the probability of passing in examination and failing in examination is not same, and that's why this classical definition is not applicable in such case. That means ideally you will not get such type of the sample space always, and in that case classical definition fails. Second one is that we want n, because in the probability classical definition of probability is m upon n, so we require m as well as n. So here to find out the probability, sometimes this n, that is total number of possible outcomes, is infinite, and if it is infinite, that is tends to infinity, then we cannot find out the ratio m upon n and we cannot find out the probability. So example is tossing a coin until head appears. So until head appears means h, th, tth and all these things. So we don't know exactly how many outcomes will be there. So in such situation, n is infinite and we cannot find out the ratio m upon n, and that's why P of A cannot be calculated. So that is the limitation. Third one is we want to find out the probability, we need n. So if the actual value of n is not known, then probability cannot be computed using the classical definition. Example, in the experiment of capturing fish from the pond, the total number of fish in the pond is not known. So if you are going to fishing, how many fish you have catched, that you can count. But actually in the pond, we don't know how many fish are there. So n is unknown. So n is unknown, and that's why we cannot find out the ratio m upon n. So here these are the three major limitations of classical definition. Now let us go towards the probability model. Let omega be a finite sample space containing the points omega 1, omega 2 dash dash omega n, that is omega is equal to omega 1, omega 2, in the curly bracket we have written. So these are the finite number of elements. Assign a real number p of omega I to each of omega I. That means for every element we are having that probability, that is denoted by p of omega I belongs to omega, such that 0 less than equal to p of omega I less than equal to 1 for I is equal to 1 to up to n, and p of omega 1 plus p of omega 2 plus p of omega 3 plus p of omega n, that is equal to 1. That means sum of all the probability is equal to 1. So p of omega I is called as the probability of the elementary event omega I. So this is the individual probability of the element, and this is the sum of all the probabilities in omega. So the sum of all the probabilities of the omega is always equal to 1, and probability always lies in between 0 to 1. So individual probability or the probability of the event also. Now when you want to check whether the given is a probability model or not, you will always check whether the first condition, that is probability of omega I, that is every element lies in between 0 and 1, and second thing, the sum of all the probability must be equal to 1. If the first condition itself fails, then no need to check the second condition. Now see the example. P of omega 1 is equal to 0, P of omega 2 is equal to 0, P of omega 3 is 0, P of omega 4 is 0, P of omega 5 is 1 by 2, and P of omega 6 is equal to 1 by 2. Check whether it is a probability model. So that means in omega there are totally 6 elements, and you want to check whether it is a probability model. So the first one case, that each of these probability is either a 0 or greater than 0. So the first condition is satisfied. Now consider the sum of all the probabilities. So p of omega 1 plus p of omega 2 plus p of omega 3 plus p of omega 4 plus p of omega 5 plus p of omega 6. Now substitute the values and take the addition. So addition is coming to be 1. So sum of all the probability is equal to 1. So both the conditions are satisfied, and therefore it is a probability model. Now see the second example. P of omega 1 is minus 1 by 3, P of omega 2 is 2 by 3, P of omega 3 is 0, P of omega 4 is 1 by 3, P of omega 5 is 0, and P of omega 6 is equal to 0. Check whether it is a probability model. Again this omega contains 6 elements, omega 1, omega 2 up to omega 6. Now see here, in the first itself, first check the first condition, that is probability is greater than 0 or not. Now here P of omega 1 is minus 1 by 3. So P of omega 1 is minus 1 by 3. So which is not positive, that is less than 0. So the first condition itself fails. So no need to check the second condition. So it is not a probability model. Now see the third example. P of omega is 1 by 4, P of omega 2 is 1 by 4, P of omega 3 is 1 by 4, P of omega 4 is 1 by 4, P of omega 5 is 1 by 4, and P of omega 6 is also 1 by 4. Check whether it is a probability model. Now see here the first condition, all the probabilities are 1 by 4, so it is greater than 0, so it is satisfied. Now see the addition of all the probabilities, P of omega 1 plus P of up to P of omega 6. So 1 by 4 plus 1 by 4 plus 1 by 4 plus 1 by 4, so it is equal to 6 upon 4, and 6 upon 4 is greater than 1, so it is not equal to 1. So though first condition is satisfied, but sum is of all the probability is not equal to 1, so it is not a probability model. So like that, when the values of each element is given and omega is given, then you can check whether it is a probability model or not. Now let us turn towards the probability of the event. So Probability P of A of an event A is the sum of probabilities of the elements in A. So P of A, by notation it is denoted as sum of all the P of omega I, where omega I belongs to A. That means you will add the probabilities of the elements which are in A only, that is nothing but P of A. Now there are some axioms of probability. So the first in these axioms, let omega be a finite sample space concerning to a random experiment A, an event on omega. We define P of A, that is the probability of A. It is defined as any real valued function on omega which satisfies the following axioms. The three axioms are, first one is 0 less than or equal to 0 less than equal to P of A less than equal to 1 for each event A in omega. So we know that probability of any event always lies in between 0 to 1. So probability of are real numbers and that are in the closed interval 0 to 1. Second is that the probability of the axiom second axiom is probability of the sample space, that is omega, is always equal to 1. And the third axiom is if A and B are mutually exclusive events in omega. Mutually exclusive means A intersection B is equal to empty set or phi. Then P of A union B is equal to P of A plus P of B. So this can be generalized, that is in general if A1, A2, An are mutually exclusive events on omega, means A1 intersection A2 intersection A3 intersection An is equal to empty set. So in that case P of union of Ai is equal to sum of all the probabilities of Ai, that is P of union of Ai is equal to summation I is equal to 1 to n of P of Ai. So these are the three axioms. By using the three axioms we can solve the problems and we can give the proofs of some probabilities. So there are some now let us see some theorems related to this probability. So first theorem is probability of A complement is equal to 1 minus P of A. Now let us see the proof. We know that A intersection A complement is phi always. That means A and A complement are mutually exclusive, as well as we know that A and A complement are exhaustive also. That means P of A union A complement is equal to omega. Now let us take the probability of both the sides. So P of A union A complement is equal to P of omega. So A and A complement are exhaustive as well as exclusive. Therefore by axiom 3 we can write P of A union A complement as P of A plus P of A complement. That is equal to, by axiom 3 P of A omega is 1. So write this P of omega as 1 by axiom 3. Now this P of A complement, keep it here as it is. Take this P of A to the RHS. So P of A complement is equal to 1 minus P of A. So that is the proof of the first theorem, that is P of A complement is 1 minus P of A. Now second theorem, that is probability of an impossible event is always 0. Impossible event means phi. So P of phi is equal to 0, that we want to show. Now we know that phi complement is omega. So take the probability of both the sides. So P of phi complement is equal to P of omega. But just now we have proved that is probability of A complement is 1 minus P of A. So instead of A we can substitute phi. So 1 minus P of phi complement is nothing but 1 minus P of phi. And this P of omega is always 1. That also we know by axiom 3. So 1 minus P of phi is equal to 1. So this 1 minus this 1 and this P of phi that we can take to the RHS, that will become positive. So P of phi is equal to 1 minus 1 and 1 minus 1 is 0. So probability of the empty set is always 0. Obvious it is, because we know that empty set, that means m is equal to 0. So by definition we m upon n, 0 upon n, that is 0 always. But here we can prove it by the using the these identities. Now third theorem, for any event A of omega, 0 is less than equal to 0 less than equal to P of A less than equal to 1. Now consider the proof. So we know that A and A complement are exclusive as well as exhaustive. So exclusive means A intersection A complement is phi and A union A complement is equal to omega. Again, by first axiom we know that probability of any event is always positive. So P of A is greater than or equal to 0. So this first part, that is 0 less than or equal to P of A, it is obvious here. Now similarly, P of A complement is also greater than or equal to 0 by axiom 1. But we know that P of A complement by theorem 1, it is nothing but 1 minus P of A, which is also greater than or equal to 0. Why we have 1 minus P of A? Just now by theorem 1 we can write it. So by theorem we have P of A complement is nothing but 1 minus P of A, and that is greater than or equal to 0. Now take this P of A to the RHS. So P of A is greater than or equal to 1. So this is call it as 2. So combine 1 and 2. One says it is greater than 0 and second says that it is so here P of A is less than or equal to 1. So combining 1 and 2, we are having 0 is, so 0 less than or equal to P of A is less than or equal to 1. Now let us turn toward the next theorem, that is, if A is subset of B, then probability of A is less than or equal to probability of B. So Venn diagram we can also show, or it is very obvious because number of elements in A is less than number of elements in B. So that ratio m upon n will be less than their m upon n for B. So that is an obvious one. The next theorem is, that is, probability of A union B is equal to P of A plus P of B minus P of A intersection B. This is also called as the theorem of total probability. So the theorem of probability, that is total probability or addition theorem. So P of A union B is equal to P of A plus P of B minus P of A intersection B. Now let us see the proof of this. We can show these two sets here we are considering, that is, they are not mutually exclusive. That means there are some elements common between A and B. So if two events A and B are such that they are not disjoint, means they are not mutually exclusive. So we can draw the Venn diagram, that is, these two circles means set A as well as set B. So we get the three parts. First part is A intersection B complement, second is A intersection B, and third one is A complement intersection B. Now we know that all of these three parts are mutually exclusive, but their union is A union B. So here first part is A intersection B complement, A complement intersection B, this one and this third one A are mutually disjoint because there is no common element between these three, that is orange, green and blue. So we have A union B is equal to this A intersection B complement union A complement intersection B union A intersection B. Now take the probability of both the sides. So P of A union B is equal to probability of this whole RHS. Now we know that if the events are mutually exclusive, then by axiom 3 we can write, instead of union we can write the addition of probability. So P of A intersection B complement plus P of A complement intersection B plus P of A intersection B. Now call it as 1. Now see here, again with the see the Venn diagram, this A event is nothing but the union of this orange part as well as green part. Orange part means A intersection B complement and this green part is nothing but A intersection B. So we can write this A as A intersection B complement union A intersection B and take the probability of both the sides. So P of A is equal to P of A intersection B complement union A intersection B complement. Now again by axiom 3, instead of union we can have the probability addition. So P of A is equal to P of A intersection B complement plus P of A intersection B. So call this as a equation 2. Similarly here, this B is nothing but the union of the two parts, that is green, that is A intersection B and A complement intersection B. So this B can be written as A complement intersection B union A intersection B, and therefore P of B is equal to, take the probability of both sides, so P of A complement intersection B union A intersection B. Now again, since these are mutually exclusive, by axiom 3, P of B is equal to P of A complement intersection B plus P of A intersection B complement Now we got the three equations, that is this equation 1, equation 2 and equation 3. Now we will do the addition of this second and third. So if you are going to add second and third, so second is P of A and third is P of B. So here in LHS, P of A plus P of B. Now write down all the RHS of equation 2. So that is P of A intersection B complement plus P of A intersection B. Now then P of A complement intersection B plus P of A intersection B, that is RHS of third. Now P of A intersection B, P of A plus P of B is equal to, now I will keep all the first three terms in one bracket, that is P of A intersection B complement plus P of A intersection B plus P of A complement B in this square bracket, and then P of A intersection B as it is. Now see, this bracket quantity is nothing but the RHS of equation 1. So for this we can write as a LHS, that is P of A union B. So from 1 I can write it as this square bracket as P of A union B and this P of A intersection B as it is. So by using this we got P of A plus P of B is equal to P of A union B plus this third term, that is P of A intersection B as it is. Now we want to find out probability of A union B. So keep it in the one side and take the remaining, that is P of A intersection B, to the LHS. So P of A union B is equal to P of A plus P of B minus P of A intersection B. So that is the proof of this theorem. Now there are some inequalities also related to probability which we required for solving the examples. So if A and B are the two events defined on omega, then P of A intersection B is equal to minimum of P of A and P of B. And second one is P of A union B is always less than or equal to maximum of P of A and P of B. So third one is P of A union B is less than or equal to P of A plus P of B. Fourth one is P of A intersection B complement is equal to, this is the formula, that is P of A minus P of A intersection B. And fifth one, P of A complement intersection B is equal to P of B minus P of A intersection B. So by using these inequalities and the formulas, we can solve the examples on the depending on the probability. So in the next lecture we will see the examples on the probability. Till then, bye. Thank you.